Hey everyone, this is our Engineering 6 project team for the Arbitrary Wave Function project. My name is Samir. I'm Armaan.
I'm Tabib. First, we're going to show you the GUI for the actual app. This is the GUI. Um, we have a term slider for the number of terms you could choose for your function. The more terms you choose, the more accurate it's going to be. We have a slider for cycles, for the number of cycles you want to appear in your graph. We have a frequency knob, we have amplitude knob, we have a DC shift knob, and we have a duty cycle knob, and this is in percentage. So if you wanted to graph the sine function first, we would such as the sine, we would graph this, and you can see it graphs. If you wanted to change the number of cycles you want the graph to show, like we could have 4 cycles instead of 5, we would change that, and then we would graph it. And then the code for this, before I show you the code for the sine, I want to show you the buffer that the TA gave us. So this is the buffer code. It gives us the sample rate to help us determine the interval for the actual wave. Uh, if the frequency gets really high, the graph looks very inaccurate. So we made an if and else function, and if the frequency is below 150, the interval is 1 divided by the app rate, and if the frequency is really high above 150, the interval is 0.0001. And then so this is the code for the sine function. The t for the sine is just set up as from 0 to 10, and the interval is this interval determined here. It's the one defined here. And this is the equation for the sine function, in which f is the frequency determined above, and then this is our for loop to sum up the actual terms. Oops, oh that's for rectangles. So this is we don't have a for loop for sine, but this determines the amplitude, or it applies in the amplitude, and this applies in the DC shift to shift the graph up and down. So a sample graph would be DC shift of 5, amplitude of 5, and graph that, and you see how it changes. And then for the rectangle, it's the same thing. The interval is the same. For the terms, we're adding every odd number of terms because the rectangle graph is an odd function, and this is just a for loop to sum up all the terms and whatnot. And so yeah, this is the function for it, and then this just applies the DC shift. This applies that in the for loop that amplitude is applied. So if you were to graph the actual function, we would change it to rectangle. Let's say we wanted 5 cycles instead of 4, and then make 1 terms, and that's how the graph looks like. If you want it to be more accurate, you just change the number. Then it doesn't change much, but yeah.
So this is our code for the triangle waveform function. It's similar in concept to the rectangle function in that we're summing up all the odd terms, since the triangle function is an odd function. And this is the function that was provided to us in the project manual. And this is our for loop to sum up all the odd terms. And the DC shift shifts the sine function up. So if we were to graph the triangle function, this is what it would look like. And then obviously we can change the number of terms, which fluctuates the accuracy. And this is to change the number of cycles. And we also have our sawtooth function here. Um, for this sawtooth function, we're summing up all the every single term, since this is an even function, and this is the equation for the sawtooth function, and this is what it would look like if we were to graph the sawtooth function. We change the number of cycles, change the accuracy. And this is our equation for the full wave. Just like the sawtooth function, we're summing up all the every single term within our for loop. And this is our function.
So for one of the special features, it's a pulse wave function, and it works similarly to the rectangle one, except you can change the width of the high voltage, and that's done by taking the period and taking the width of the period, or the width of the high voltage, and then we multiply by the desired duty cycle, which is a percentage of the width of the high voltage, and then we put it into this equation, and it sums up the terms, and it does pretty much the same thing, except you can, for example, change the duty cycle to 10%, and it would be very narrow, or you could change it to 80%, and it would be very wide. In order to make the cycles graph the amount of cycles you want, we have this part of the code which takes the number of it takes one period and multiplies it by the desired number of cycles. So this is how we plot it. And we also added another special feature, which is sound. And what it does, it is takes the complete sound graph and plays it at the rate that was given by our buffer code. And these are global variables because we need to move the variables onto the next callback function. And they're written, these are the global variables, or they're, yeah. So this is how the sound works. Let's say we want random frequency, a rectangle, we'll graph it, and then play the sound. And then if you want to do sine wave, a triangle, sawtooth, full wave, and pulse wave. And this function runs until, it runs for around like 10 seconds until you want to stop it. So this one can play as long as you want, and then you can stop it. And that's pretty much all our project.